Welcome to our fourth STEAM project, based on the BBC Microbit, the Geek Pi microcar and MakeCode, in which we will make our robot car follow the light. This course is at the introductory level. We actually assume that you don't have any prior knowledge of programming, sensors or actuators. We call this level the Scout level. My name is Peter. I am the founder of Educommando and a certified STEAM instructor and course designer. In this project, we will learn how to work with a special kind of resistor, the LDR or Light Dependent Resistor. We will capture the readings of an LDR. We will compare the readings of the two LDRs of the microcar, and we will transfer the difference between the LDR readings into a DC motor action. As always, we have quite some experimenting to do, so let's get started. This is an LDR. LDR stands for Light Dependent Resistor. It is a type of resistor that changes values depending on the amount of light that falls on it. The brighter the environment, the more light will be caught by the resistor and the value will go down. The darker the environment, the less light there is and the higher the value will be. You can clearly see this when we measure the value of the resistor expressed in ohm with a multimeter. The robot car has two LDRs in the front, one on the left side and one on the right side, taking the forward direction of the car as the starting point. The left LDR is connected to pin number 4 and the right one is connected to pin 0. Remember those pin numbers because we'll need it in the programming. This is very useful because we can compare the readings of both LDRs and instruct the car to either go to the left or to the right depending on the LDR reading. Of course, to make the microcar move, we need to activate the motors. Let's first take a quick look at the inside of a direct current electrical motor. These are probably the most common motors you will find in cars, cycles, fans, and so on. This model shows the inside, the permanent magnets, the coils with the windings, and the connectors to the power source. When attaching a battery, the motor starts to run. Reversing the polarity of the battery reverses the direction of the motor. The Geek Pi microcar has two motors. Each motor is connected to 2 pins, so 4 pins in total. The left motor is connected to pin 13, which will make the motor run backward. Activating pin 14 will make it turn forward. The same for the right motor, which is connected to pins 15 and 16. Making one wheel spin forward and the other wheel not, or even backwards, will allow the microcar to turn left or right. Once again, remember those pin numbers. That's it for looking at the parts and the components. Time to do some programming. Here we are in our Microsoft MakeCode environment. We create a new project, so we hit the Create button and we give the project a meaningful name like Microcar Light Tracking. I hit the Create button and here we are in the programming environment with the on start and forever blocks already present. For this particular project, we don't need to install any extensions, but because we link the BBC microbit to the robot car, we know that there is a potential of conflicts between pins that are used by both devices, specifically conflicts at the level of the 5x5 LED display of the microbit. To avoid that, we go to LED, select More, and take LED Enable and drag and drop it into the On Start block. Make sure that it remains on false because it disables this LED 5x5 display. Our second step is to program the motors. Programming here is defining the direction of the microcar. Going forward, backward, forward left, forward right, and stop. 5 different situations that we can define upfront, and we do that by defining a function. And where do I find the functions? Well, you will find it under Advanced. When I click on Functions, you see that there is a black bar with nothing in, with the exception of Make a Function. And that is because we have not yet used a function in this particular program. So I select Make a Function, and I have to give the function a name, and let us start with the obvious one. We call it forward. In this function, we will set the pins 13, 14, 15, and 16 in such a way that the car will move forward. And forward is achieved by activating pins 14 and 16. So how do I do that? Well, under pins, there is a command that says digital write, and I'm going to drag and drop it into this part. Now, I'm going to change this to pin number 13, and I'll still leave it to 0. I have to do this for all the 4 pins that we have defined, or that are needed for our motor. So 14, 15, and 16. Now we know that we have to activate 14 and 16, so I'm going to set 14 to 1. And I can do that by using this little slider, or I can just type 1. That will make our motor and our microcar to move forward. So the left and the right motor will both be initiated to move forward. Creating the other functions is just a matter of copying the forward function and renaming it into something else. So I'm going to copy and paste the forward function. As you can see, it gives it automatically a name that I can override. I'm going to use it. I'm going to call it backward. To make the car run backwards, it means that I have to activate pins 13 and 15 and deactivate the pins 14 and 16. Voila. I'm going to copy paste again the function, and I will make my canvas a bit smaller, which will make it easier to follow. put this on side. And I'm going to call this left. To go to the left, I need to, what do I need to do? Well, I need to only activate one wheel. So to go to the left, I need to activate the right wheel. And the left wheel will stay still, will not move, so that it acts like a pivot around which the microcar can turn. So the left wheel has to be to 0, has to be set to 0, so pin 14 has to be set to 0, and pin 16 will be set to 1, so the right wheel will continue. And I can do it here by simply clicking the value to 0. The right one will be just the opposite, so rename this to right, and here it's going to be pin 14 that has to be activated, and pin 16 will be set to 0. And then we can also introduce the full stop, and that's quite easy because the stop simply means that all of the pins need to be set to 0. With this, I have my 5 movements that I want to have for this particular exercise. So we can go to the next step. For this moment, let's leave these functions and let's take a look at our LDRs. Just as we have written a 0 or a 1 to the motors by using a digital write command, now we want to read the value from the pins 0 and 4 to which the light-dependent resistors are attached. And most importantly, we want to compare the two values with each other. So to decide whether the car will go left or right will depend on what is the highest or the lowest value that is being transmitted or measured from the LDR 0 or LDR 4, pin 4 or pin 0. And how do we do that? Well, we will find all of that in the block logic. And here is the logic. And I'm going to take this one. So if true, then what's going to happen? Now, we are not going to use true as a statement because we want to compare two values. And where do we find those two values? In the comparison, and here is a comparison. And I can change that true statement as another statement. Now I have if 0 equals 0, then something will happen. So 0 will need to be replaced by the readings of the pins, the pin 0 or pin 4, and it's going to be either not equal to, but smaller than or smaller than equal to, and then something is going to happen. Where do I find the readings? Well, the readings are found here under pins. And it's going to be an analog read. So I'm going to click the analog read of pin 0, and I want to compare it with the analog read of my other pin, the analog read from my pin number 4. Okay. Now, here is something maybe a bit complicated. We have just said that the LDRs, the more light gets on the LDR, the smaller the resistance value becomes. the less light, so in darkness, the LDR will get a very high level, a very high ohm value. Now this does not mean that when the P0 level is smaller, the reading here is smaller than the P4 reading, we need to turn that once again upside down, because the readings is a value between 0 and 1023. And here it's again that the highest reading will reflect the most light that comes out of it, because the resistance is the lowest. So when the analog read pin is smaller, so P0, which is the LDR on the right side, when that value is smaller, it means that less light is there. So when P0 is smaller than P4, it means that it will go to the LDR P4, which means that it has to turn to the left. And here I'm going to call my function. I'm going to call to the left. And if that's not the case, then it's going to go to the right. So once again, function, I'm going to call my function, and I drag and drop it here under the else statement. Now, theoretically, this would and this will work, but in practice, we will see that the robot car will follow the light source and it will be very erratic. So it will turn to left and right all the time, but the result will be that it starts to run in circles. And to avoid that, we can add some additional delays, and also we can include that a part of the car drives straight forward between the different readings. So what we can start is that I start my forever loop with a function. I'm calling a function, and I can start my forever loop by just saying call forward, which means that when the program starts, the car will move forward. Now, I don't want the car to move forward forever. I want to do that for a certain period of time, let's say 2 seconds. And I do that in the basics. I have my pause block and I put it here, and I'm changing it to 2 seconds or 2000 milliseconds. Then it starts the reading, and it's going to the left in case that the P0 reading is smaller than the P4 reading. So I'm calling the left function, and I'm going to do the same trick here. I'm going to do a pause for, let's say, 1 second. And after that, I'm going to say, you have turned for 1 second. Now you can drive straight on again. So I'm going to call the function forward again. Here it is. Else the car is going to the right. Once again, I'm going to put a pause of 1 second. And then I'm going to call the function forward again. And that's it. What will happen with these small adaptations is that the car will run a bit smoother. Let's give it a try and see whether it works. Okay, I have downloaded the program and I've picked up the car. I'm going to switch it on, and as you can see, it's quite a sunny day, so I'm going to darken the P0, which means that it's going to go to the left, and if I'm going to darken the P4, it has to go to the right. And it's doing that. Yep, it seems to be working. Let's now move to a darker area and see how it reacts to my flashlight. Here we are, and as you can see, it's a bit clumsy in recording, but I think you get the point. If I really light into one of the LDRs, it is moving into the direction of that LDR, which is exactly what we wanted to accomplish. That's it for this project. What else can you do? Well, you can add, for instance, the OLED screen to display the left and the right readings of the LDR. You can link the readings of the LDR to, for instance, the RGB LEDs. For instance, you can program it in such a way that the lights will turn on when darkness comes, and it will turn off when there is sufficient ambient light. And you can play with different values as thresholds to trigger an action. This is also a great project to teach your students about light. For instance, explain the speed of light versus the speed of sound. And actually, that would be a great introduction to one of our next lessons, where we will use an ultrasonic sensor to avoid obstacles. That's it for project number 4, in which we were able to make the microcar chase the light. I hope you and your class enjoyed this as much as I did. In our next project, we will continue to control the motors of the car, but this time through the active infrared sensors, so that the car can follow a black line. Bye bye for now.